There are a couple more things about the weak interactions that we haven't discussed yet. I guess really more details about basic particle physics that I've been hiding from you up to this point that we now need to bring onto the table. First of all, we discussed weak interaction decays. For example, the decay pi minus goes to mu minus neutrino, or neutron going to a proton electron antineutrino. And we discussed these in terms of a weak interaction current, which coupled U to D, the left-handed parts only, or nu mu to mu, the left-handed parts only, things like that. So the weak interaction theory that we've developed so far doesn't have any place in it for some other decays that are known in nature, like K minus goes to mu nu or E nu. Baryon decays like lambda going to p pi minus. So what's going on here? The K minus has in it a strange quark and an anti-up quark. And what has to happen for this process to occur is that the strange quark has to annihilate the anti-up quark and turn into a purely leptonic final state. Similarly here, the strange quark has to turn into an up quark to make the proton and give off a pi zero. So, well, what can I say? We've got to put something in the theory that allows these processes to occur, because manifestly they occur with strengths that are close to the typical strength of the weak interaction. And then there's one more odd detail that we also ought to account for. At the same time that we need strange goes to up plus a W boson, which can then go to leptons or quarks, we can't let strange go to down plus a Z boson, which might, for example, go to mu plus mu minus. That doesn't happen. Or rather, it happens with some very suppressed process. So just to give an idea, the branching ratio for the process K0 goes to pi plus mu minus nu. Did I get that right? Yeah. Is 27%. The branching ratio for K0 goes to mu plus mu minus is something like 10 to the minus 8. So somehow we have to build a theory where this kind of process can occur easily, but this kind of process can't occur. And eventually, as you'll see, the standard model takes care of that problem. Okay. Well, first of all, what we ought to do is to try and understand better the phenomenology of kaon decays. So let me just write down a few formulae that are actually useful in that respect. We can measure the intrinsic strength of the strangeness changing weak interaction, this process, in the following way. If you look at K goes to pi mu nu, this is like kaon beta decay. It's really the analog of this process over here. The way it works, this guy so this guy will contain, for example, an up quark, let's say this is a K0. It'll contain an up quark and an anti-strange quark. This can go to something that contains an up quark and an This can go to something that contains an up quark. No, I'm sorry, I'm all messed up here. an up quark and an anti-up quark, and a mu and nu. And so these things come from a W. This transition must come from a current. And that current must come from a matrix element that looks something like this, where we have U bar gamma mu S. Presumably, it's just the left-handed part to be consistent with the rest of the weak interactions, and K. These guys here are spin zero states. This is a vector current, so there's not so much that you can write for this. You really have to write something like this, pk plus p pi times some form factor f plus of q squared, where q is pk minus p pi. That's the invariant momentum transfer in this process. You could also write another term with pk minus p pi that turns out not to be important, because we're going to dot this with a Feynman diagram where if we dot this into the muon final state, we're going to get 0. So then what you can do is to measure the size. Well, so now we can ask, what is the size of this quantity? And I claim that at 0 momentum transfer, this is just, this object would just be a flavor current, an SU3 flavor current. These are states of definite SU3. And so what we're doing is just measuring the SU3 charge, basically, of the kaon and the pion. So at q squared equals 0, this quantity F plus has to be 1. And so if I now take that and put that into my calculation, I could try and make a new term in the weak interactions that looks like this. So I'll take the current J plus, which changes S into, and I'll add a term which changes S into U. And so we had before the term U bar gamma mu D here with coefficient 1. Now I'm going to add a term that changes U, that allows U to change to S. And if I use that as the matrix element, I plug it in here. I take the vector part, which makes the transition between K and pi. I use the fact that at Q equals 0, I'm just measuring the SU3 charges of K and pi. This quantity then at Q squared equals 0 has the value 1. I measure the rate, and in fact I can even measure it as a function of the momentum transfer. Using this normalization, we can then determine the coefficient that goes in front of this term in the weak current. And that coefficient turns out to have the value 0.2237. It's rather accurately known, plus or minus 0.0013. One needs to make all kinds of corrections that I haven't discussed to reach this level of accuracy. That is the correction to this formula, which you can work out from strong interaction theory. But nevertheless, this number is really known quite accurately. Okay, now, we've started monkeying with the weak interaction theory. Last time we just had this. Now we have this. Can we stop there, or do we need to monkey with it some more? Well, actually, in the 1950s, when people really looked in detail at the V minus A theory of weak interactions, there was another problem that people noticed, which seemed to be a problem with the theory of neutron beta decay. So in the same way that I can try and use SU3 to determine, to get some kind of normalization of the matrix elements of this current, and thus determine the coefficient that goes here, I can use SU2 to get some normalization of this current and figure out whether what goes here is really 1. Maybe I should add one more term. There's a term here with the muon and the electron. And what I'd like to say is that what stands in front of these terms is actually 1. And then it's an experimental question whether what stands in front of this term is 1 or whether it's some different number in terms of the normalization of, for example, the muon decay rate, which is known very precisely. Yes?
Okay, so we're only allowing the U left-handed to change to an S left-handed as well.
Right.
Why is that? This question, why can't we change the left-handed to right-handed?
Oh, well, if we have a current, the current conserves helicity. So if this is a left, that must be a left. Now, I could put S right here and U right. So that would, you could call that a right-handed weak current. And you could search for those things experimentally. They really seem not to exist. Okay. Okay, so now we come to the question, yes?
I don't really understand what you mean by changing from like to a strange.
Sorry?
What do you mean by changing it to a strange?
I can change, a U to a strange or a strange to a U.
And that's because you added.
That's because I added some term. So there are processes that happen in nature. I'd better account for them in my weak interaction theory, so I really need to add that. And what I'm telling you is that the coefficient of that term in relation to the strength of mu decay is known very precisely.
What was the reason we didn't write that before?
I just forgot about it. Okay. I was trying to simplify the theory as much as possible. Okay. Now, what about this coefficient? Well, that coefficient we can determine in a very similar way. I could, for example, look at a nuclear transition which has I3 equals plus 1, and over here I3 equals 0, and even parity in both cases. So that means only the vector current should appear. The vector current here is U bar gamma mu d, and once again, this is the isospin current. So this matrix element should be proportional to the, basically, this Clebsch-Gordon coefficient, which is just the square root of 2. And that's it, times the 4 momentum of this nuclear state. And so in that way, you can get a very good normalization of this term in the weak current relative to the rate of mu decay. That is, if I look at, let's call this state A, let's call this state B. If I look at A goes to B plus electron plus antineutrino, and I measure the rate of this beta decay process relative to the rate of mu decay, I can get a very good idea of what this coefficient is. And if I call that coefficient VUD, VUD is very, very close to 1. But it turns out not to be exactly equal to 1. It turns out to be 0.97 once again, the modern determination, 0.97418 plus or minus 0.00026. So it's almost 1. What I told you on Friday was almost correct, but it differs by a few percent. And around 1960, nuclear physicists worked incredibly hard to estimate all the isospin breaking corrections to these matrix elements. But somehow they couldn't make this couple percent deviation of VUD from 1 go away. So what can you do about this? Well, in 1963, a fellow named Debo had a very interesting idea. He noticed, and maybe I should say that I've given the modern experimental values of these terms. The situation was nowhere near so clear in 1963. Debo noticed that VUD squared plus VUS squared was equal to 1. That is, that the presence of this term could potentially explain the discrepancy in this term from 1. And so what he did was to write VUS is equal to the sine of what we now call theta c, the Cabibbo angle, and VUD is the cosine of theta c. And the fact that this cosine is less than 1 is accounted for by this term. And indeed, if you plug in these numbers, what you get is 1 minus 0.0004 plus or minus 0.0007, I think. So experimentally, it really does seem to be true that this Cabibbo hypothesis matches up. And so now we have a new expression for the weak current, the isospin raising weak current. So we have the electron neutrino, the muon neutrino, and the muon, everything left-handed. We have U bar, gamma mu, and what it does is that it couples to a linear combination of D and S. And when I make this particular linear combination, the coefficient here is really 1. And I think if you think back over what I did in the past couple days, you'd realize that if this is really an SU2 Young-Mills theory, these coefficients all have to be equal. They all have to have the strength of the charge G. So now whereas if there were a discrepancy here, we'd be in trouble with the interpretation of this theory in terms of Young-Mills theory. As long as the coefficients are all equal, so the W has a universal coupling, Young-Mills theory is still good. Yes?
Is the Cabibbo angle like a constant of nature?
We'll get there. Before the end of the lecture, I will explain to you where it comes from. Well, I won't really explain to you where it comes from, but we'll push it back one way. Okay. Now, this is great, except that there's another problem that you have to worry about. So now what we see is that the up quark can turn either into a down quark or into a strange quark. So this is good and bad. It's good because we can now explain one more aspect of weak interaction phenomenology that I haven't explained to you yet. So if I look at a K0, the K0 can decay to pi plus pi minus, for example, through this weak interaction process that I've described. This guy has in it a down quark and an anti-strange quark. The strange quark can turn into an up quark. So this is du bar. And then if I add, I guess, so this can turn into du bar and then ud bar. And this has the right quantum numbers to make this final state. So by a weak interaction process, I can turn this into this and decay it. Now, in a similar way, I can decay the K0 bar, which has SD bar, to this final state. And if I can do those things, I could also do the reverse. And so there's a weak interaction matrix element that's second order in the weak interactions that can change K0 into K0 bar, or vice versa. Now, this, it turns out, leads to some incredibly cool physics. Let's say I shoot a proton beam on a target, and a proton has mainly quarks. So what will come out is a beam which contains more K0s than K0 bars. That I more often get the down quark than the anti-down. So let's just roughly say I can shoot a proton on a target and get out a beam of K0s. Now, the K0 can decay, but it can also turn into a K0 bar. And so down the road here, what we have are some mixtures of K0 and K0 bar. Well, now let's just think about that a moment. There are two linear combinations, K0 plus K0 bar and K0 minus K0 bar. The K0 and the K0 bar are particle-antiparticle, so they have the same mass. So actually, this system starts out degenerate. And then if there's a transition amplitude from K0 to K0 bar or vice versa, I get a very small mass splitting. And in fact, let me write down the numbers. The mass of the kaon is 498 of the K0 is 498 MeV. And the mass splitting between these states is 3.5 times 10 to the minus 12 MeV. So that's a very small mass splitting. Actually, it's such a small mass splitting that this mixing process is macroscopic. It takes place over centimeters. So you make a K0 beam, and over some distance of centimeters, it resolves itself into these two eigenstates. Now, one of these eigenstates, so CP will change this into that, or that into this. So these states are odd parity, and C, it interchanges them. So CP will change the K0 into, I guess, minus the K0 bar, and we'll change the K0 bar into minus the K0. So what that means is that one linear combination, namely this one, has CP equals minus 1, and this one has CP equals plus 1. Okay, now, this 2 pion state over here, pi plus pi minus, has CP equals plus 1. That is, each pion is odd under parity, and they're interchanged by the operation of C. So only this state can decay to pi plus pi minus. This state can't. Yes?
How do we know what particles change under parity?
Well, you look at their couplings. So, for example, if you have a decay rho to pi gamma, then the structure of that amplitude is different depending on whether the pion is an odd parity or an even parity state. Although in the quark model, any fermion, anti-fermion bound state has odd parity, so the quark model also tells you that pions have odd parity. But originally that was determined experimentally by looking at some scattering amplitudes. Okay, so pi plus pi minus in any event obviously has CP even, because no matter what the parity is, I get 2 factors of that, and then C interchanges them. And similarly, pi plus pi minus pi 0 has CP equals minus 1 if the pion is odd parity and I add 1 more pion. So apparently then this first guy, which I'm going to call Ks, can decay to pi plus pi minus, and K0L can decay to pi plus pi minus pi 0. And if CP is conserved, it can't happen the other way. So this is now pretty weird, but also interesting. So you make a kaon beam, you make a proton beam, and K0 mesons and K0 bars come out the other end. Then what happens is that within a few centimeters, I get lots of decays to pi plus pi minus. So basically, anything in the linear combination corresponding to Ks decays to pi plus pi minus. Now, pi plus pi minus pi 0 is a three-body final state. So here you get two-body phase space. Here you get three-body phase space. And further, 3 times the pion mass is pretty close to the kaon mass, so it's a restricted three-body phase space. So this decay takes about 1,000 times longer. And so over a few centimeters, all the k shorts decay. Then I'm left with a beam of pure k longs. And then over 10 meters, the k longs decay to 3 pions. Weird, but correct. I mean, that's actually what you observe. Okay, we'll come back to this phenomenology in a moment. By the way, this neutral kaon system is really fascinating, and those of you who are interested in particle physics should learn more about it. But I'm going to stop talking about it now for a moment. But I'd like to point out that there is a problem with the system, namely in the smallness of this number. So let's try and compute that number from Feynman diagrams. The first thing we could do is just have the process that I mentioned before. We have S d bar, or maybe ds bar. And then we imagine some weak interaction process where the S turns into a U bar, and a D. I form these into pi mesons, and then I go back. And then I can consider this to be the imaginary part of some phenomenological Feynman diagram. I could try and construct the real part and get an answer for this transition amplitude. And the answer I get is of the right order of magnitude to be this number. But there's a way to get a much larger answer, which is to consider this Feynman diagram. Where I put an up quark here, and then I put W minus and W plus on these two lines. Now, the problem with this Feynman diagram is that it's divergent. I've got the integral d4k. I've got here 1 over k squared squared. For the quarks, I have another k slash over k squared. And, No, this is fine. So I'm not going to get a divergence. I'm going to get something, well, I'm going to get a divergence if the mass of the W goes to infinity. Then I only have this stuff. So I have 4 k's in the numerator and 2 k's in the denominator. And I'll get something that would diverge if the mass of the W were infinity. If I take this thing into account, the diagram is still convergent, but I'm going to get something that, that counts out in the following way. There's a g to the 4th. There's, because of this integral, a 1 over mw squared. And then at these vertices, there's some factors of VUD and VUS. So you get VUD squared and VUS squared. And now if you look at this, this is more or less the Fermi constant times the quantity alpha weak. So the size of this thing is that it's proportional to the Fermi constant squared. But this diagram is only proportional to one factor of the Fermi constant times a numerical suppression of about 100 or so. And it's just not enough. This diagram is enormously larger than the number which is measured. So what can you do about that? Well, this was a problem that basically was maintained for a long time. People proposed, for example, that the W mass was extremely small, maybe just a few GeV. So you'd get more advantage from this suppression when you computed this diagram. Finally, Glashow, Iliopoulos, and Maiani came up with the right answer. What they proposed was that there was another quark. So Glashow, Iliopoulos, and Maiani proposed that we were missing some term in this Lagrangian, that if we added it, we could solve this problem. But that term involved another quark. So they wanted to add, they postulated the quark C. They added the following term, minus sine theta Cabebo D plus cosine theta Cabebo times S. And always, everything here is left-handed. So now this has the following very interesting effect, that if I compute this diagram, let's just look at the top row, for example. It's proportional to VUD times VUS, or let's write this out. This is the cosine of the Cabebo angle, the sine of the Cabebo angle. Now, if I add this term, and I ignore for the moment the mass of the charm quark, then I get, from this expression, at this vertex, I'll get minus the sine of the Cabebo angle, and I'll get plus the cosine of the Cabebo angle. And then these two terms would exactly cancel. In the full diagram, I'd get a double cancellation if I could put U and C in any position. And then instead of the answer I got over there, I'd get alpha weak times G Fermi times UDS, VUD, VUS squared. And then these two contributions wouldn't cancel only by virtue of the charm quark mass. So I'd get a power of the charm quark mass divided by MW, and I'd get that for each side. So what they concluded was that if the W mass is where it's supposed to be in the Glashow-Weinberg-Salam theory, this was all in 1970 before the W had been discovered, but the charm quark mass was only a GeV or so, then I'd get enough suppression to explain this number. So out of the blue, they postulated, at that time only the strange quarks were known, that there was actually another quark, a fourth quark called the charm quark, and that it had this particular kind of weak interaction. And of course, as you all know, because I've explained it to you in the first week of the course, people then discovered the charm-anti-charm bound state, J psi, and the whole family of so-called charmonium states, the whole basically hydrogen atom of charm and anti-charm. And these guys were dramatically right, and then one could go on and found the standard model. So this is interesting, but it's a little weird. This is actually the correct, or almost the correct structure of the weak interaction current, but it has this mixing angle called the Cabebo angle, and we have to figure out where that comes from. So let's now discuss that. And the first thing I need to do is to tell you about something that I've been resisting telling you about for a couple days, which is where the masses of quarks and leptons are in the standard model. So there's definitely a problem with constructing the masses of quarks and leptons in the standard model. Let's just start with the leptons. The leptons, the left-handed leptons, are in a doublet with isospin 1/2. The right-handed electron has isospin 0. The term I want to write for the mass of the electron is E bar E, which is E bar left E right plus E bar right E left, this term here manifestly violates SU2 because it combines something which transforms under weak isospin with something that doesn't. And I just am not allowed to write that term if I want to write a gauge invariant Lagrangian, which is gauge invariant under the weak interaction SU2. So how can I solve that problem? Well, the solution was actually given in the original papers of Weinberg and Salam. We used the Higgs field to give mass to the W and Z, and I explained to you how that worked on Monday. The Higgs field also, it turns out, has exactly the right quantum numbers to give mass to the electron. And the Lagrangian that I would write instead of this one would be the following one. Delta L is equal to lambda E times E bar left, or rather L bar, this whole doublet, dotted into the Higgs field, times E right plus Hermitian conjugate. So now, this term would look like nu bar E bar left, and then the Higgs field. And now if I give the Higgs field its vacuum expectation value, then from that term I would get a term lambda E over the square root of 2 times only the E bar left, the neutrino would be left out, V E right, and that's exactly of the form that I'm looking for. And I would decide that the mass of the electron was equal to lambda E times V over the square root of 2. I haven't really explained the mass of the electron, but at least I've converted the mass from a dimensionful number into some dimensionless coupling constant. Oddly, the value of this coupling constant, I told you V is roughly 250 GeV. The value of this coupling constant is 10 to the minus 5. So I still have to explain why that number is so small. But with a formula like this, I can generate the mass of the electron by spontaneous symmetry breaking. So I think what you would say is we can generate the masses from dimensionless couplings of the quarks and leptons to the Higgs field. Those dimensionless couplings shouldn't be larger than 1. And maybe they can be as small as you like if they're suppressed in some way for some of the generations. And so now maybe what I should do is to write you the complete coupling that we would need to explain the masses of all the quarks and leptons. We would write something like this, a coupling of lambda L, L bar, let me write lambda I, L bar I times the Higgs field times L right, and I goes over E mu and tau. We would then write the same thing for the down quarks, Qi times phi times D right I. And now please notice Q is the doublet UD for the ith generation. So I here goes over ds and b. This only gives mass to the down quark. It doesn't give mass to the up quark. So we still need to write one more term, which would be lambda ui times q bar I. Now q bar I, let's write its index alpha. That goes over 1 and 2, the upper and lower components of the doublet. If I write epsilon alpha beta phi star beta times u right, this now raises the vacuum expectation value from the bottom to the top. So this will give mass to the up quark. And now what I'd like you to notice is that everything is working out right. So the Higgs field here has a hypercharge. So the isospin manifestly works out. The hypercharge is a half. The hypercharge of this guy is minus a third. And the hypercharge of this guy is minus a sixth. So everything works out to 0. This is invariant under both SU2 and U1. Also invariant under color, maybe I should say. This guy has hypercharge plus a half. This is plus a half, and this is minus 1. So again, the hypercharges work. This guy has hypercharge minus a half, minus a sixth. This is plus 2/3. So here we need hypercharge minus a half. And please notice that the complex conjugate of the Higgs field has the opposite hypercharge, so that will supply it. So this Lagrangian here is perfectly SU2 cross U1, actually cross color invariant. And if we spontaneously break the symmetry associated with the SU2 cross U1, this term can give mass to all the leptons, this term can give mass to all the down quarks, and this term can give mass to all the up quarks. We have to explain still what the values are of these dimensionless parameters lambda u. An interesting clue is that if the mass of the top quark is 170 GeV, which is what it is, then lambda t is of order 1. So one of those couplings is of order 1, and the rest just get progressively smaller. And why that is just frankly not understood. But at least everything kind of fits into this picture. We just have to explain where these dimensionless couplings come from. There are lots of theories, but I think it's fair to say no one really understands it. OK. Now, this is not the most general form of the Higgs coupling that one could write down. And at this point, there's a very interesting exercise to do to write the most general possible form of the Higgs couplings allowed by SU3 cross SU2 cross U1 and think about what its implication is. Oh, maybe I should say one more thing. I've left out the term corresponding to this for the neutrinos because I didn't put any right-handed neutrinos into the standard model. If you put that term in, you might get masses for the neutrinos. The kind of coupling you would have to put in front of that is 10 to the minus 12. So let me just leave this aside. Let me leave the right-handed neutrinos out for the moment. That will have a very interesting consequence, as we'll see. OK. So what I'd like to do then, please remember this structure. We're going to come back to it. Is that I'd like to write down not a particular form of the Higgs coupling to quarks and leptons, such that I need to make the masses of the quarks and leptons. I'd like to write down the absolutely most general form allowed by gauge invariance, and then we'll see what we can do with it. So the most general form is the following. I need something which is SU2 cross U1 cross SU3 invariant. And that already, as you can see, really restricts me to the kind of structures that I've written on this blackboard. So the most general thing I can write is lambda L is now generalized to a matrix. I could have arbitrary mixing of the 3 lepton generations. And this can be a general 3×3 complex matrix. And from the point of view of gauge invariance, there's no reason not to write the most general 3×3 complex matrix here. Similarly for the down quarks, and similarly for the up quarks. the really strong assumption I'm making now is that there's only one Higgs field. If there's more than one Higgs field, this can get a lot more complicated. Plus Hermitian conjugate. And I'd just like to remind you that in terms of these fields, the kinetic energy terms are much simpler. The kinetic energy terms are things like L bar I d slash L and Q bar I d slash Q and U bar right I d slash U right, etc. So these are absolutely diagonal in the generation quantum numbers, and all with coefficient 1. And because the gauge fields are in here, there's universal coupling to the gauge field, which is also diagonal. So this part is extremely simple and really dictated by the structure of Yang-Mills theory. But this part up here can be as complicated as you want with general 3×3 complex matrices. However, if I have a general 3×3 complex matrix, I can always write that in the following way. As a 3×3 unitary matrix, a diagonal, a real diagonal, actually a real positive diagonal 3×3 complex 3×3 matrix, and a second 3×3 unitary matrix. So roughly, you would take lambda L lambda dagger, that's Hermitian, so you can diagonalize it, and that tells you what U is. You would take lambda L dagger lambda, you diagonalize that, that tells you what V is. If I take out U and V, the result has to be diagonal. It also has to be real because the eigenvalues are the square roots of the eigenvalues of these matrices. If there are any phases or negative signs, I can pull them into U and V. So this structure is a completely general one. Unitary, real positive diagonal, unitary. Okay. Well, that's cool because now we can eliminate U and V by making changes of variables on L and L. Namely, if I write V dagger times LR is equal to my new L, and U dagger L is equal to a new L, then this term up here takes a much simpler form. It takes the form D, maybe I should call this Y. Y I L bar I times phi times L I. And in terms of these new fields, this is totally diagonal in flavor. The y's, which are the eigenvalues of this matrix, are just the individual masses for E, mu, and tau. Further, I can actually remove the matrices U and V from the whole rest of the Lagrangian. So for example, if I look at the photon coupling is, or let me just look at the SU2 coupling. So SU2 doesn't couple, so I'm looking only at this thing here. I have L bar I A mu A sigma A over 2 times L. If I change L to L prime, this U matrix just goes right through and commutes with these guys. Please notice that here I'm making the same change of variables on the lepton as on the neutrino. So U commutes with SU2, and the U just goes through. So this is A mu A sigma A over 2L is equal to the same expression in terms of the L primes. So now I can write the entire Lagrangian in terms of L primes. And now this is diagonal in flavor. This whole term is diagonal in flavor. The Euclid coupling is diagonal in flavor. There's no more flavor mixing. So it's actually a prediction of the standard model that if you write down the most general structure consistent with gauge invariance, and then you just make an appropriate change of variables, that E, mu, and tau are not connected by any interaction. So electron number, muon number, and tau number, after this change of variables, are exact symmetries of the standard model. You remember I told you on the first day that the muon decay involved 2 neutrinos, and that the muon decay just without neutrinos was highly forbidden, with a branching ratio of less than 10 to the minus 11. We've now explained that by using the gauge structure of the standard model. Okay. Well, now we can do the same thing for quarks and leptons. In the same way that I did here, I could write, please excuse me, U lambda d is equal to UD times YD times V dagger d. I could write lambda U is equal to YU VU dagger. And I can, in the same way, make this Higgs coupling here and this Higgs coupling here flavor diagonal. So now the Higgs field coupling to between the left-handed and the right-handed quarks is totally flavor diagonal and has no ability to change flavor. However, please notice that because both of these terms are present, I really need to make different transformations in general on the down quarks and the up quarks. So that has a definite consequence if we think about the W and Z interactions. For the Z interactions, the Z couples to, as you remember, up left times the thing I wrote last time, QZ left times gamma mu U left, plus U right, QZ right, times gamma mu times U right, plus a similar thing for the Ds. This thing, remember, is this funny factor that I talked about in the previous lecture. Okay. Now, in this term, if I change from the U's to the U primes, it only involves the matrix VU. And so if I change to U prime, what I'll get in here is VU dagger, and that's equal to 1 if VU is a unitary matrix. Similarly, in this term, I'll get UU dagger, and that's equal to 1. And so in the Z couplings, this change of variables just disappears. The various terms that we found completely disappear from the Lagrangian. So the photon and the Z coupling are both completely diagonal in flavor. And this explains this funny fact that there is no transition from S to D plus Z, which can go to mu plus mu minus, creating a decay, for example, K0 to mu plus mu minus. It turns out that this decay can occur through a higher order Feynman diagram, like that one. But the rate is extremely small, and it's consistent with the highly suppressed number that you get from experiment. So the absence of this decay in the Lagrangian is actually, again, explained by the gauge structure of the standard model. Now, the one place where you get into trouble is in the W coupling. The W couples to UI gamma mu di. In the fundamental Lagrangian, it couples to this. If I make this change of variables, this is equal to UI left bar prime then I'm going to get a factor of this factor here, VU, gamma mu, D left prime, and I'm going to get a factor of VD. And I'm sorry, I think the daggers go here. So if VU is not equal to VD, that is to say, if this matrix is diagonal in a different basis from this matrix, I'm actually going to get something left over here. But what I get left over is a 3 by 3 unitary matrix. And that occurs in the W coupling, but it doesn't occur in any other coupling in the standard model. So very weirdly, the W coupling is allowed to violate flavor, but with an appropriate choice of and changes of variables. The Z coupling, the photon coupling, the Higgs couplings, all can be made flavor diagonal. The individual lepton families are not connected to each other after we've made this change of variables. So when I go to the mass basis for the leptons numbers are all conserved. When I go to the mass basis for the quarks, that is, I diagonalize these matrices, there's one source of flavor mixing that still remains, which is this V that appears in the weak interactions. And this V is called the Kabibo-Kobayashi-Maskawa matrix. I've told you who Kabibo is, but I need another couple minutes to tell you who Kobayashi and Maskawa are. Okay? So you are allowed to have strange to U charged currents, but not strange to D neutral currents. The standard model, that's just a property of the standard model. And that is in more or less exact accord with what we see experimentally. Okay, well now I have to tell you one more thing about this VCKM. Let's consider, first of all, the 2 by 2 case. So up, down, charm, strange. This is where we got to in terms of the phenomenology that I was describing earlier in this lecture. So I can take a completely general 2 by 2 unitary matrix. It has 4 parameters. And I can write those parameters in the following way. Cosine theta, sine theta, sine theta, cosine theta. So now I'm trying to write the most general possible form of VCKM for 2 generations. And then I can put a phase here. I can put a phase here. I could put a phase here. But by unitarity, this phase is now determined. These 2 rows have to be orthogonal to each other. So this has to be e to the I beta minus alpha plus gamma or something like that. So a 2 by 2 unitary matrix has 4 parameters, and I've written the 4 parameters explicitly here. You're happy? No, U2. U2. Sorry? Oh, here I wrote SU3. I should have written U3. Okay. Now, there is a problem with the difference between U3 and SU3 that has to do with anomalies. And let me just say that's beyond the scope of this lecture. You can ask me about that privately. Okay. Yes?
In this exposition, you basically also made terms with up and down, but I guess there are similar terms for the other terms as well.
No. Here I'm thinking about this as a 2 by 2. So this would act on D on this side. So this is D and S. And on this side, it acts on U and C.
Yeah, I was more talking about the terms of the top, like this lambda times U.
Here? Where? Here?
Yeah, there.
Here? So I and J here would go over U, C, and T, actually, in the full standard model. 3 generations.
Oh, so Qj is actually corresponds to what, or
Yes. Yeah. J runs over the 3 generations. So for the moment, I only want to think about 2 generations. Okay, so this is the most general form of the CKM matrix that could appear in the weak interaction Lagrangian for 2 generations. Now, I'd just like to notice that if I make the following definitions, if I let U go to U, so this is U prime already. If I let U prime go to U double prime times e to the minus I alpha, this is bar. If I let C prime go to C double prime times e to the minus I gamma, then I can soak up the alphas and gammas. If I let D prime go, I think, to e to the I beta minus alpha, something like that, then I can soak up the betas. Now, an overall phase change has no effect. But for 2 generations, I have 3 phases that are not overall phases. So I can soak up all of the phase factors in this expression. And the final expression is cosine theta, sine theta, minus sine theta, cosine theta. And this leads to a weak current which couples U, C, D, and S exactly the way that Glashow, Iliopoulos, and Maiani wanted. So actually, that structure is exactly what comes out of the most general form possible of Higgs couplings in the Standard Model, where theta C is the Cabibbo angle. And now, this is very important. These parameters are all real. So it turns out that if you do a CP transformation on the theory, the entire theory in these new variables is CP invariant. Actually, CP invariance is a very natural property of gauge theories. C, as you know, takes a particle to an antiparticle. P is a parity reversal. So if I start with completely massless particles, for example, a left-handed fermion, C will take a left-handed fermion to a left-handed antifermion, and P will then take a left-handed antifermion to a right-handed antifermion. But this guy is the antiparticle of that guy. So in a gauge theory, I would just have this interaction, and this interaction would contain the left-handed particle, but also the right-handed antiparticle, and it would be perfectly invariant under the combination of C and P. Similarly, if I write F right here, I would have the multiplet F right and F bar left, and the kinetic energy term that's required in Yang-Mills theory would be perfectly invariant under a CP transformation that interchanged these 2 states. The only possibility for CP violation in the Standard Model is the Higgs couplings, the Yukawa couplings, but a CP is only violated if the Yukawa couplings are imaginary. So when I transform particles into antiparticles, I would get the complex conjugate of one of these expressions, but something funny would happen with the coefficient. Another way of thinking about it is that CPT is always a symmetry of any Lagrangian theory. And if I do a T transformation, that is anti-unitary. That would complex conjugate the coefficients. So a complex coefficient would be odd under T. But somehow we've gotten rid of all the complex parts of the coefficients. This interaction is completely real. And so for 2 generations, the Standard Model just has the property that it's automatically CP invariant. Whatever we wrote down in the beginning, we can always make a change of variables to a set of variables where there's a well-defined CP symmetry, which is a symmetry of the Lagrangian. Okay, now this would be great except that CP is violated in nature. And this was learned in a very beautiful experiment done in 1964 by Christensen, Cronin, Fitch, and Turley. And it involved this neutral kaon system that I told you about before. So what they did was that they set up this neutral kaon system the way that I described. You hit protons on a target. You let kaons decay to pi plus pi minus. You're then left with a beam which is pure K0 long, the CP, so-called the putative CP odd eigenstate, which can only decay to 3 pions, and which therefore lives 1,000 times longer. You then very carefully go 10 meters out here, and you carefully observe the decays of the K-long beam. And what these guys noticed is that 10 to the minus 3 of the time, you observe the decay K-long to pi plus pi minus. Okay. That's CP odd. That's CP even. CP must be violated. Okay. Now we're in big trouble, because I've just told you that there's this incredibly successful model of weak interactions which explains everything, but a consequence of that is that it is totally impossible within that model to have CP violation. So you need to expand the model in some way in order to allow a CP violating interaction. And so after thinking about this very hard, Kobayashi and Maskawa in 1972, so this is before the discovery of the charm quark, they knew about Glashow, Iliopoulos, and Maiani, but that was just a speculation at that date, made the following extended speculation, that if you get 2 more quarks called B and T, then you get a 3 by 3 matrix. A U3 matrix now has the following number of parameters. It has 9 parameters, which are in the form of 3 angles plus 6 phases. But now if I have 6 quarks, I can only remove 5 phases by a field redefinition. So the trick I used here doesn't quite work. There's 1 phase angle that's left over. And so they made the bold suggestion that there weren't 4 quarks. Remember, at that time, there were only 3 quarks known. They said, oh, yes, Glashow, Iliopoulos, and Maiani are right. There has to be a 4th quark. But then there have to be 2 more quarks, because if you have 2 more quarks, we have a mechanism for having CP violation. And with that, we can explain all the CP violation in nature. So, well, is it right? Well, now this matrix that I wrote before is extended to a 3 by 3. And let me write the form of it over here. One can write an approximate representation after you remove all the phases in this way. This is a very useful parameterization. Lambda is the Cabibbo angle. And the matrix written in this way, so up here you would have A lambda cubed rho minus I eta. And down here you would have A lambda cubed 1 minus rho minus I eta. So that's a representation of the matrix which has the following properties. First of all, it's unitary up to lambda to the fourth, where lambda is the Cabibbo angle, which, remember, is a small angle whose sine is something like 0.2. And secondly, the phases are pushed into the corners. So manifestly, the phases can only appear when you have processes with bottom quarks or top quarks. And the values of these parameters are hierarchical. So lambda is 0.2, A is of order 1, and rho and eta here are also of order 1. So there's a natural hierarchy of these flavor mixings. Yes? Rho and eta are some parameters. So there are 3 angles and 1 phase, so there are 4 parameters in all. And I've taken those 4 parameters to be lambda, A, rho, and eta. And eta is the CP violating parameter. OK. So now the question is, can this matrix explain all CP violation in particle physics? And so it turns out that if you compute the extra diagrams for K long, K short mixing, using top quarks in here, as well as up in charm, this matrix element has an eta in it. So it can give a CP violating mixing. So it can tell you that K long and K short are not exactly CP eigenstates. Well, so far so good, but that's very indirect. But one prediction of this theory is that CP violation should be much, much larger if you have bottom quark decays. Because if you have bottom quark decays, you can then take advantage of a term like that directly to create a manifestly CP violating process. And in fact, all the details are in the notes. I need to stop now, but let me just tell you. Biji and Sanda noticed that there are some specific decays of the bottom quark, relatively rare decays with branching ratios of order 10 to the minus 3, for which CP violation would be 100% effect. Accelerators were built at SLAC and at KEK in Japan to test this hypothesis. Those accelerators produced billions of bottom meson pairs. The decays of these bottom mesons were observed in a very careful way. These special modes were uncovered. And when people looked at the CP effect in these special modes, it was found that indeed, most famously in the decay, B goes to J psi plus a K short, that there is an of order 100% effect by which this process is not equal to this process in order 1. And that is a very direct test of CP violation through these 2 interactions and allows you to measure eta. And in fact, the corpus of these measurements, which I've included in the transparencies, really narrows down on specific values of all 4 of these parameters. And everything we know about CP violation in elementary particle physics reactions is consistent with values of these 4 parameters occupying a very narrow region of their parameter space. OK, well, this is now the complete standard model, and it answers all of your questions. And if you don't think so, come and ask me after the lecture. OK, we'll go on tomorrow to some more stuff. Yes?
How do you know that the interaction K0L to pi plus pi minus isn't just extra long-lived states of K0S?
Because the K0S has a finite lifetime. So the number of K0S's decreases exponentially.
So the numbers just don't.
So yeah, I mean, if there are only 2 linear combinations, there are only 2 quantum states. If CP is conserved, one is CP even and the other is CP odd. The CP even guy can decay to pi plus pi minus, and then you just have exponential decay. So yeah, you just have to get very, very far away so the exponential is incredibly small. And if you still see something, that means it must be coming from the K0 long. And if you doubt that, you just go further away and you ask whether there's anything there. The number should just decrease exponentially. That's just quantum mechanics.
And it stays the same the further out you go.
It stays the same the further out you go. Well, it decreases exponentially with the K long lifetime. That's okay. And there are other very cool effects, some of which are described in the lecture notes, which I don't have time to discuss. Okay. Good. See you tomorrow.